Hey folks, welcome to this week's information visualization lecture. This week we're going to talk about how to explore a data set when it just doesn't quite make sense to you. What are some of the tools and tricks you'll need to do to get your head around it? But first I think we need to address the elephant in the room. This course is about to take a bit of a pivot. We've spent the first little while talking mostly about how to design with data, and thus far we've avoided the question of what that data means, how to work with it on its own terms. I got some bad news for some of you. That will involve a little bit of mathematics. But I got a promise for you. We will make this journey into the world of statistics as palatable as possible for a design audience. Because it's a bit similar to the argument that you would have had made to you a couple of years ago for design programming. It's just not feasible for you to be a good designer of digital products and services, apps, websites, etc., without knowing a bit about how they're made. You're not necessarily going to go on to be a mobile app developer yourself. But if you don't understand how they work and what's done on the device and what's done on the server and how they talk to each other and just a little bit about how to make that kind of thing, maybe how to throw together a prototype, then you're really not going to be the best person for that job. The same applies to data visualization designer. We are not going to force you to become statisticians or data scientists, but if you want to work on how to present data to tell a story, you need to understand that data. And for this course, there are three things that it's going to be necessary to get your head around. The first one is just enough statistics to not trip yourself up, and that's the purpose of this week's videos. The second one is a little bit of programming to help prepare and present data programmatically, rather than using tools like Infogram. And the third one is just enough of an understanding about machine learning and AI algorithms that when you go out into a world that is increasingly powered by those, you will be able to work with them too. I think these things are both exciting and approachable and palatable to someone who is a keen designer. They are not turgid, dull, chalkboard in cast law subjects, or at least they don't have to be. So let's tackle this. Exploratory data analysis is about as close to discovering design thinking as statisticians ever get. Let me show you a quote from a design pioneer and person who wrote that book I showed you back there. John Tukey said, "It's far better to have an approximate answer to the right question than an exact answer to the wrong question." Part of being a designer is making sure that you have found the right problem, that you have framed it in the right way, because then solving it will be something that's possible. What Tukey's saying is you need to really actually understand your data and explore your data, even if that means you have to be vague and approximate. And it turns out there's a pretty simple and approachable set of tools for doing that. For the examples I'm going to be going through in this lecture, they are drawn from Our World in Data's excellent GitHub repository. We're going to be using this particular one, which talks about carbon emissions and GDP coupling, so the relationship between those two. This is not something you're going to be working on in the tutorial. The tutorial exercise is focused on something else. But if you want to grab this and follow along with the sorts of things that I'm doing, go right ahead. Not at all required. This is what that data looks like. It's so messy you can't even really see it. I mean, I probably could have scaled the text up, but you know what I mean. The blue bars are the GDP per capita. Specifically, they are the GDP per capita of that country between 1990 and 2013. So it's a change over a 23-year period. The orange data shows the change in carbon emissions per capita, that is per head, right, per person, over the same period. So the way this stuff is calculated is it is the carbon emissions for the whole country divided by the number of people in that country, and then this is the ratio between the 2013 number and the 1990 number. So when something says plus 100%, what they mean is that it's doubled since 1990. When something says minus 20%, it's gone down by 20% since 1990. If you just look at it here, though, there's really no story. There's not much to see. You can see, well, I guess most of them are hovering around or slightly below 100, but there's these huge ranges and it's not really clear what's going on. If we want to dig into this, we are going to have to do some elementary statistics. And as I said, don't be too afraid of that. It's not going to turn out to be that hard. We have a series of 3 questions that are going to, in principle, sound a bit similar to how you approach any design project. And if you think about it, back in the lecture on how to do user research, how to frame and understand a data visualization project, which I think was week 2, back on the mapping lecture, we talked about how you needed to think about stakeholders, or rather audience, and the context that they're in, as well as the data. The data itself has to be part of that exploration process. And at the time, I didn't really explain how you might go about exploring the data. Well, now we're going to do that. We have 3 questions that we primarily want to ask. How would we describe this data, that is, summarize it? What are the simple descriptive things that we can do? And the second one, how is it distributed? And I'll talk a little bit about what a distribution means, but effectively means over the axes that you've got. It is a nice, like, simple bell curve. Does it sort of slide off to one side with long tails? Has it got like a couple of humps in it? Is it just total noise? All of these things describe distributions, ways that the data varies across certain axes. And then the third question is, how do the variables in the data relate? So we have a bunch of these columns, but is there anything between them? Are they totally separate from each other, or does one help you guess the other? We're going to talk a little bit about what that means in the second video of today's lecture. But let's start at the top. How do we describe this data? And the simplest way to think about that is, what's the center, right? Like, what's the average? Now, you might remember from, I don't know, it might be year 9 maths, something along those lines for those of you who went to high school in Australia, comparable period for those who went to high school elsewhere. But there are a couple of different ways to describe the middle of some data, the mean, median, other things like mode, etc. We're going to focus just on mean and median here. They are the simplest and most commonly used. Think about this histogram, this sort of chart of number of people on the y-axis and the number of books they've read in the last year. You can see this is a pretty normal distribution. That is, it forms a nice little bell curve, right? Normal is just a statistical word, by the way. It means simple. It doesn't mean that everything should be normal or anything that isn't normal is unusual. It just says, oh, here's a particular distribution, a particular way that we expect data to behave if there's one common sort of center to the data and some fairly random way in which it varies from that data. And most things vary a little bit from that data and some things vary more. That's just going to produce a bell curve, right? The things along the bottom show that most people read about 8 books a year, and in this case that is both the mean and the median. There are going to be some resources at the end of this video, so if you are confused already at mean and median, do not freak out. At the end of the video, there's going to be a slide sending you to stuff that'll help you out immensely. And if you're thinking, oh, mean and median is easy, but then I get 2 slides further and you start panicking, then those resources have got you covered as well. The mean and the median are actually different ways of calculating the middle of data, and sometimes they are not the same. If you think about this version of the same data, same question, let's assume that this was the data for 2020. And as a result, there's some portion of people who decided that the thing they would do in lockdown, the thing that they would do during the pandemic, is to read a ton of books. And so what you see here is that while the left-hand side of the distribution looks about the same, and the people over there have read, a small number of books, some people read 1, most people read 6 or 7, there is actually a big long tail out towards the higher numbers, showing that some people read 15, 16, maybe even more. This chart looks like it's potentially been truncated. So what that means, when you've got a skewed distribution, when the tails on either side aren't the same, is that the mean and median tend to diverge. For a refresher, Median is the middle number. If you write them all out in order, 1, 2, 4, 6, 6, 6, 7, 9, 12, the one in the middle will be the median. Whatever the value of the one in the middle when they're all lined up is the median. It is the quote-unquote center of your data. Whereas the mean is calculated by summing them all up and then dividing by the number of data points. So that's kind of the default way of thinking about an average. But it turns out, if you have a couple of huge outliers, either really high numbers or really low numbers, they don't affect the median at all, because the median only cares about the middle. You can have like 1, 5 million, 5 million, 5 million, a trillion, and the middle number is still 5 million, right? It doesn't care about what the 1 and the trillion are at the other ends of that. But you can equally have that same data set of 4.9 million, 5 million, 5 million, 5 million, 5.1 million. They'll have exactly the same median, right? Because it doesn't matter what's at the ends of the list. The median just looks at what's in the middle. Comparatively, if you look at the mean would change substantially under those circumstances, because a trillion is so very much more that when you added a trillion to the other 15 million and one, that would massively skew where your mean is, and your mean would shoot off towards the right-hand side of the distribution, as it has a little bit here. Now the median is up a bit. You don't have to understand these things in great detail. You don't really have to think about what are the formulas or how I would calculate each one. But since you're going to be using these ideas to describe your data, it's helpful to have an intuitive grasp of what each of these things is. I find it useful to talk about the minimum and the maximum data points. That's easy, it's the highest and the lowest ones. The median is the one in the middle. And then it's actually useful to think about what are the ones halfway in between. So you can split your data into quartiles. That is, 25% of the data is in the first quartile, then the next 25% of the data is in the next 25%, 25%. And then you can say, what's the data that's a quarter of the way through my list if I were to put all my data points in order? A quarter of the way through this one, you can see is, I don't know, 6 and a bit maybe. There'd be about a quarter of the data points on the left of that and 3/4 on the right. And the median is halfway through, so that's 8. And then the third quartile, so that's 75% of the data would be on the left, is 9.5 or something or other. I'm guessing based off this chart because I don't have the exact numbers, right? Now you can think, oh, looking at those numbers, I can see my data is pretty evenly dispersed. Whereas if it had a really fat tail on one end, really long tail going off to one side, then the quartile would move and the maximum would be way further out. So now just using these 4 or 5 numbers, I can get a bit of a picture of what's going on in this one column of my data. Now we're looking again at the change in GDP and carbon emissions 1990 to 2013. So this is a relatively complicated data set that I just grabbed off the internet because I thought it could tell an interesting story, but it started out kind of a mess. And we can look at those 6 numbers. So we can look at the minimum. Well, the smallest number in each of these is actually negative. So there's at least one country that reduced its carbon output by 67% between 1990 and 2013. Spoiler alert, that wasn't actually because they did a great job of any kind of sustainability projects. It's because their economy cratered and all industrial activity fled the country. It was a result of war rather than a result of a good Green Deal. Similarly, there are countries in there that lost almost half of their gross domestic product, which is a devastating outcome for an economy. Remember that a recession is when a country loses any GDP. So that's when GDP growth goes negative, even a couple of percent. It's considered a recession. The first quartile starts to tell a different story. So 25% of the countries, a substantial number of the countries, had GDP growth less than 32%. So that's a whole bunch of them are positive. So we can look at that and we can think, well, actually, way less than a quarter of our data is probably negative. There's not that many countries that have lost GDP, which is good because losing GDP tends to be a pretty bad thing for a country. I am not the world's biggest fan of runaway capitalism, but GDP growth does tend to correlate with quality of life. If you look at carbon instead, you can see that the first quartile is still negative. So this is actually at least 25% of the data, if not slightly more. 25% of these countries had a reduction in carbon emissions over this 23-year period, which is great because only some of them had a reduction in carbon emissions because of war and a massive collapse of industry, etc. The median and the mean, it's interesting to look not only at what they are, so plus 50% GDP over 23 years is about normal for this data set. And for carbon, a growth of about a third in carbon emissions is normal. That gives you an idea of the scope of the problem of actually substantially tackling climate change, that over a 23-year period, most countries put on at least a third. The mean in both cases is higher than that, substantially higher than that, which tells you we have a bunch of positive outliers skewing the data to the right. So we know that we have a long tail of high numbers because our mean is higher than our median. If our mean was less than our median, we'd probably have data skewed the other way. So we have a long tail of low numbers. The third quartiles, they're actually kind of similar, right? So the third quartile of GDP is about 100%, so about a doubling over this period, and the third quartile of carbon emissions is 91%. So what we're looking at here is that there is at least 25% of the countries in this data set grew at least 90% from 1990 to 2013. And then if you look at our maximums, they're absurdly high. These are our outliers. You can see them on the chart. They're probably the first thing that jumps out. There are a small number of countries that have huge orange bars. So that's huge growths in carbon emissions per capita. Remember, this is all per capita, so per population data. So you don't unfairly penalize countries that had a lot of positive migration, for example. You would expect their GDP to grow more, and you would expect their carbon emissions to grow more because they now have substantially more people. But by focusing on the per person numbers, we're looking at a picture of how much do people in that country contribute to global warming. And you can also see a couple of absurdly high blue numbers. No prizes for figuring out which one the huge growth in GDP is between 1990 and 2013. Anybody who's paid any attention to anything will know that the transformation in China's economy over that period was probably the most radical the world has ever seen, ever. So now we can look at this data a little bit differently, just using that summary. And here I'm dropping the mean out so that we can think just of the minimum, the first quartile, the median, so that's basically the second quartile, the third quartile, and the maximum. It might help to get rid of some of those outliers, that is to truncate that last bit. So let's just zoom in on the range up to 200%. And remember that those last two on the right there do continue up skyward. So another way to think about quartiles, by the way, is thinking about percentiles. The percentile system is just a way to get more detail than quartiles. So percentiles just divides everything into 100, and you usually say things like 90th percentile. So 10% of things are higher than this. Here we've got the 0th, 25th, 50th, 75th, and 100th percentiles for both of our series of data. I think this starts to give us a picture of what this data looks like. You can start to think, okay, well, there's some negatives, outliers in both, more in carbon than in GDP. Then the majority for GDP really sits between those two quartiles, right? So the majority sits somewhere between going up by 30-something% and going up 100%. And for carbon, the majority sits between going down slightly and going up by 75%. It's helpful here to remember that this is breaking out by individual countries and that most countries are not heavily developed. So when you're looking at a breakdown of the 200 or so countries in the world, they tend towards being smaller and less developed just because there happen to be more of those. So Germany is one data point on this list. So is the United States, so is China. There are many, many smaller countries on here, and there are many, many less developed in a traditional economic sense countries on this list. And that is probably skewing things towards the higher numbers in both of these categories. So now I think we can start to answer that question of how is the data distributed, and we can put together a histogram and put our means and our medians on it. A histogram is just like we were talking about with that number of books read data. A histogram is where you put together the number of data points that fall in a particular range. That set of ranges is called bins. So instead of showing the actual data, you drop it into bins and you say, in this case, well, there's like 5 countries that are less than 25%, and then there's like 8 countries that are in this range and 12 countries that are in this range, and so on and so forth. If you can do a histogram and one of those 5-number summaries and look at your variables like this, you really have a pretty good idea, not just how to describe your data, but how it's distributed. So we can take a look at this second question now, and we can say, all right, the vast majority of countries in terms of GDP have around about 25 to 50% growth. There's a huge spike in that range. Then there's a long tail off to the right of countries that have, 50 to 75, and then all the way up to 125 or so, and then it starts to trail off there, and a short tail to the left. I would say the vast majority of countries are somewhere between 0 and 100, and most countries are somewhere between 25 and 50. You can have a look at that, and you can get some idea about what the range actually is. Where do most countries fall? Looking at carbon is actually a little bit more complicated. It doesn't seem to follow a nice simple peak as the other one does. You've got kind of fairly spread out numbers. You might start to say that there's 2 groups here, maybe. It could be just noise in the data. It's hard to say exactly, but I think you could say that there's a whole bunch of countries in the negative 25% to 0. So a whole bunch of countries that slightly reduced their carbon emissions. And then there's a broad set of countries somewhere between that 0% and 75%. So there's a ton of countries that increased a bunch, but it's not anywhere near as smoothly distributed as the GDP numbers. I think now, looking at this and looking at our means and our medians, by the way, here are the medians here. Obviously, the median number for the first one is somewhere between 25 and 50, closer to 50, I think. And the median number for the second one is in that big group there, closer to 50 again. These visualizations we've produced, by the way, are not something that you would show to a customer or your audience to try and sell them on something. We haven't thought about how to tell a story with these. These are not designed visualizations. These are visualizations we made for ourselves. We built these to understand the data. And now we understand the data, we'll be in a position to build better visualizations going forwards. The means, I left out the means. The means, of course, being slightly higher than those medians because of the right-hand tail, that is the skew towards a couple of very high numbers in both cases. Mean being affected more by outliers, countries like China, India, etc., that experienced absolutely crazy GDP growth over this time as they pulled their very large populations out of abject poverty, but also huge growth in carbon emissions as they did so, even when calculated per head, because, of course, a modern Western style lifestyle just happens to use a lot more energy than a rural pre-industrial one does. I'm in an office right now surrounded by about 15 computers with a whole bunch of fluoro lights, a fancy video camera, an air conditioning system, an office phone that honestly I haven't plugged in because I don't really like getting phone calls from the university. But however you want to cut it, there is so much data supporting my existence, and thereby, by some extent, your existence too. I even have UV lights so that I can keep my plants alive because my office doesn't have any exterior windows. Check this out. I even use energy when I'm not in the room. Does that expenditure of energy help me feel okay about working in a building when I have no exterior windows? Yes, it does. Does it make my office look nice? Yes, it does. Does it contribute to global warming? Yes, it does. These are just part of the decisions that we make when we are living industrialized Western lifestyles. And the more people in this world who we can allow to make those choices, the more people in this world who we can bring into a modern way of life, the better we will be for the flourishing of the human race. We just have to figure out a way to do it that doesn't end the planet. That last 15 seconds was not part of the course. That happens to be my personal politics. I hope you can separate it from the data science. We have a pretty good idea of these two data sets now. We know most of the simple stuff that you can learn from just looking at these series of numbers individually. In the next video, we're going to get into how do they relate? Is there a relationship between GDP and carbon, and how would you explore that? How would you visualize it? But also, are there some simple statistics that you can do to express the relationship between those? And then I promise we'll be done with the statistical part of this course. So, lifeline time. If there's anybody here who's watching this who isn't 100% sure that they understood everything I just said, and honestly, if you do a bit of soul searching, I think that might be a lot of us, then you need to talk to this guy. This is Sal Khan, the founder, I guess, of the Khan Academy, which I've got to say, if you haven't heard about it, is the best online resource for stuff you learnt in school and then forgot. It's used by millions, maybe hundreds of millions of kids around the world to support their learning. It has become even more critical since the pandemic forced so many of those kids to learn in part from home. But it is free and open source and not restricted to high school kids who are learning this for the first time. So everybody get on over to Sal Khan's page on statistics. This is summarizing quantitative data. It goes through these measures of the center of data, the central tendency, mean, median, etc. It goes through how to look at quartiles and percentiles. It talks about variance and standard deviation and covariance, the things that we're going to talk about in the next lecture. And it does so in a calm, approachable, example-driven way that is honestly better than any lecture or tutorial I or the tutors could put together for you. Sal Khan is a genius, and he will help you get up to speed on what I promise is the smallest set of statistics that you probably need to know to pass this course.